Hi everyone. In today's videos, we are going to talk about two types of equations, the exponential equations and the logarithmic equations. It is important that you are able to recognize which type is which so you'll know what method to apply. Luckily, it's pretty simple to tell which type is the exponential equation. The exponential equation will usually just have an exponent, a variable in the exponent, and you're trying to solve for that variable. And a logarithmic equation will have logarithms involved. So part one, solve exponential equations. I want to recall a very important property, the equivalence property, where we have if b to the x is equal to b to the y, then we can claim that x is equal to y, with the condition that b is a positive number and b cannot be 1. So let's apply that property to these problems. Part A, we have 3 to the 2x minus 6 is equal to 81. So I notice that this has a base 3, and potentially we can write 81 in terms of base 3. So we have 3 to the 2x minus 6. 81 is the same as 3 to the 4th power. And because the two bases are the same, they're both 3, so you can set the exponents to equal to each other using the equivalence property that we just went over. So this becomes a linear equation, which is pretty simple to solve. We just add 6 to both sides. So this will give us 10 here, and divide both sides by 2. So that will give us x is equal to 5. It is important that you always check your answer by plugging the value back into the equation. So we have 3 to the 2 times 5 minus 6, and we want to see if it's going to equal 81. Well, 2 times 5 is 10. 10 minus 6 is 4. So we're looking at 3 to the 4th power. Does it equal 81? It is. So therefore, the answer we got is correct. Let's try another one. So we have 25 to the 4 minus t is equal to 1 over 5 to the 3t plus 1. Sometimes it might not be obvious how we can convert one to the base of the other. So then sometimes we might use a third base, which is, in this case, is 5. Because simply I could recognize that 25 can be written as square, and then to the 4 minus t. And then 1 over 5, writing as base 5, that's 5 to the negative 1, and then to the 3t plus 1. Now this is the same as 5 to the, we're going to multiply these exponents, so that will be 8 minus 2t. And then over here, that's 5. And then we can also multiply these two exponents, so that will give us negative 3t minus 1. Well, now that the two bases are the same, we can claim that the two exponents must be the same as well using the equivalence property. So we just solve for t. I can add 3t to both sides, so that will give us t on this side, 8 plus t, and the other side is negative 1. And then just subtract 8 from both sides. Negative 1 minus 8 should give us negative 9. And of course, you should check the answer here as well. Now, sometimes we are not going to be very lucky that we can convert both sides to the same base. Sometimes it is just not possible. So then what do? Let's look at example 2. Solve for x. Give exact and approximate answers. We have 7 to the x minus 60 is equal to 0. We're going to follow 4 steps. Step 1, isolate the exponential expression on one side. So the exponential expression is 7 to the x. I want to isolate it to be by itself. So I'm going to add 60 to both sides to move the negative 60 over. So this is equal to 60. Step 2, we want to take the log of the same base on both sides. So in this scenario, you can pick the base that you want. However, because our calculator only come with log base 10 and log base e, so that's what we're going to be using. So you can do log base 10 of 7 to the x is equal to log base 10 of 60. Notice that we don't usually write base 10 if it's a common log. We just write log. Alternately, you can also use base e, so that will look like natural log of 7 to the x is equal to natural log of 60. Step 3, use the power property to bring down the exponent. So the power property says that we can move x to the front and it would look like this. Now keep in mind that log of 60 is a constant. If you put it in your calculator, it'll give you a decimal number. And log of 7 is also a constant. So to get x by itself, we just divide both sides by log of 7 because log of 7 is a constant. So we divide both sides by log of 7. So then on the left side, we just have x, and on the right side, we have log of 60 over log of 7. Now this right here is the exact answer. We could also use the change of base formula and write this as log base 7 of 60. Or you can just leave your answer this way. Now an approximate answer would be if we use our calculator and calculate this out. And if you use your calculator here, you should get 2.1041. We'll round to 4 decimal places. So this right here is the approximate answer. Let's try another problem. Part B, we have 10 to the 5 plus 2x plus 820 is equal to 49,600. So following the 4 steps again, the first thing I want to do is to isolate this exponential expression. So I'm going to move 820 to the other side by subtracting it. So 49,600 minus 820 should give us 48,780. Step 2, we want to take the log of both sides. Now here you have a choice of choosing log base 10 or natural log. I would like to choose log base 10, and it is because I see that this one also has base 10, and so maybe we can use one of the basic properties that we learned earlier, where the base of the log and the base of the exponential form are exactly the same. On the other side, take the log as well, and this is what we get. Now, one of the basic properties that we learned is if you have log base b of b to the x, that is equal to x. Notice how these two match, and the answer would just be x. So applying that, this will equal 5 plus 2x, which is equal the exponent. And that is equal to log of 48,780. Remember, log of 48,780 is a constant if you put it in your calculator. So treat it like a constant, and our goal is to get this x by itself. So first, we want to subtract 5 from both sides. So just log 48,780 minus 5. And then divide both sides by 2. So we have log of 48,780 minus 5 over 2. Now notice I didn't use my calculator to calculate log of 48,780. That's because I want this exact answer with no rounding involved. But if you were to use the calculator and calculate this out to get an approximate answer, you should get negative 0.1559, round to 4 decimal places. Next example, C, 2,000 is equal 18,000 times e to the negative 0.4t. Now, this exponent only belongs to e. It doesn't belong to 18,000. So I want to isolate that exponential expression. I want to divide both sides by 18,000. And that will give me 1 over 9. Notice that I'm not dividing to get a decimal number because I want an exact answer. And this side, 18,000 cancel, so we just have e to the negative 0.4t. Now I have two options here. I can take the log base 10 of both sides, or I can take the natural log of both sides. This time I am going to choose the natural log of both sides. And simply because I see base e in the exponential expression, and I know I'm going to be able to use this basic properties that we mentioned earlier. So on the left side, that would just be ln 1 over 9 is equal to negative 0.4t, using the same property up here. Alternately, you could also use the power property, move this to the front, so that will be negative 0.4t times ln e. And ln e is equal to 1. Again, this is one of the basic properties, and that is, if you have log base b of b, that will equal 1. And as you can see, that in the natural log, the base, it's e. So e and e match, therefore it's equal to 1. So that will leave you with just negative 0.4t, and that's what we got right here. Now, to get t by itself, all you have to do is divide by negative 0.4. I could go further and apply the quotient property for this. So that would be ln 1 minus ln 9 over negative 0.4. And on this side, I will just get t. Now remember, ln 1 is equal to 0. That's one of the basic properties. So we're looking at 0 minus ln 9. So it's just negative ln 9 over negative 0.4. Again, because this equals 0. And since they're both negative, I could just divide both of them by negative 1. So that will give us just natural log of 9 over 0.4. So this right here is the exact answer for t. And the approximate answer for t would be 5.4931. Now, sometimes you might have two exponential expressions in one equation. In this case, make sure one of them is isolated, and then we're going to take the log of the same base for both sides. So in this one, you can pick log base 10 or log base e. It doesn't really matter since neither one is going to match with these bases here. So I'm just going to use log base 10. So log of 4 to the 2x minus 7 equals log of 5 to the 3x plus 1. Again, using log base 10 here. Using the power property, we should be able to move all these exponents to the front. So in the front, I have 2x minus 7 in parentheses, and then times log of 4. And on this side, I should have 3x plus 1 pulled to the front, and times log 5. Now, at this point, we have x in two different places. We're going to somehow move them over to the same side. So to do this, I'm going to distribute the log of 4 to each of the terms in here. Now remember, log of 4 and log of 5, they are just constants. So treat them like constants. So when I distribute, I have 2x times log 4 minus 7 times log 4. And over here, I have 3x times log 5 plus 1 log 5, which is just log 5. So these two have the variables. I want to move them together on the same side. So that's 2x log 4 minus 3x log 5. And then this guy and this guy are constants. I want them to be on the other side. So I have log 5, and then to move negative 7 log 4 over, I just add 7 log 4. Okay, to single out that x, I want to factor x. And then I have 2 times log 4 minus 3 times log 5 is equal to log 5 plus 7 times log 4. Now the x only appears in one spot. I can isolate x by dividing both sides by this whole quantity, which turn out just a constant if you were to put it in your calculator. So this will cancel. That will leave x on the left, and this right here, it's our exact answer. And if you were to use your calculator and approximate this will equal negative 5.5034.